Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 5, Part 3. This is the part of the second lesson of Unit 2 on forces and energy, and it's a continuation of the section on forces, Part 2. So where we left off was the beginning of solving force problems. And this first page is basically a list of hints and strategies for solving force problems with free body diagrams and using force formulas. So obviously, number one, you want to read the question carefully. It is no exaggeration to say that every phrase within the question has meaning. Okay, so second thing you need to be aware of is what parameters do you know? In other words, what is given? What are the givens? Do you know whether there's an acceleration? Do you know the coefficient of friction? Do you know whether there even is an acceleration? Do you know if the object is moving to the left or to the right or up or down? Okay. What are you being asked for? Work backwards. What do you need? So if you need to solve for the acceleration, that means you work backwards. That tells you you need to know the net force and the mass. The mass may be given to you, but you'll need to determine the net force. Okay, how do you get the net force? Well, you figure out the forces that add up to that net force, and then you figure out how to calculate each of those. All right, number 4, what forces do you know about? Are they horizontal, vertical, or diagonal? Now, in this course, we're not going to throw diagonal forces at you. It'll be either horizontal or vertical. But if you were taking a more advanced course, you would have to take a diagonal force and break it up into two forces, a horizontal force and a vertical force that add up to that diagonal force. All right. Number 5, draw a free body diagram. This is essential for solving these problems correctly. You have to show all the forces on the object or system of objects as arrows pointing outward from that object. In other words, what is the forces doing to this object? You never need to care about what the object is doing to other things. We only care about the forces acting on the object or group of objects of interest. We call a group of objects a system. All right. Number 6, you're going to make an XY table. What is an XY table? This is a table that's broken up into a grid of four main boxes that refer to the positive and negative direction horizontal, the positive and negative direction vertical, and then there are two other boxes that express the sum of all the horizontal forces and the sum of all the vertical forces, also known as the net horizontal force and the net vertical force. Number 7 is advanced. As I mentioned, if you have any diagonal forces, you would use trigonometry to separate the original force into its component forces, but we're not going to worry about that. Number 8, determine the combination of forces equal to the sum of the horizontal forces. That's also known as the net force in the horizontal direction, or the horizontal net force, and the sum of the vertical forces, otherwise known as the vertical net force. All right, so how do you do that? You look at all the horizontal forces and you add them up. Some are going to be positive, some are going to be negative. The ones to the right are positive, the ones to the left are negative. How do you get the vertical forces? The ones that are pointing up are positive, the ones pointing down are negative. You add those together to get the sum of the vertical forces. If you already know the acceleration, some problems you'll know the acceleration, some problems you won't. If you know the acceleration, either horizontal acceleration or vertical acceleration, then you can use the mass and the acceleration to calculate the net force in that direction. This is especially important in horizontal net forces. If you know the horizontal acceleration, just multiply it by the mass, and you get the net force in the horizontal direction, and then you can use that to calculate the forces that add up to the horizontal net force. All right, scrolling further. Number 9, if there is no net acceleration. Okay, how do you know there's no net acceleration? Because you're told something is moving at a constant rate, at a constant velocity, it has a constant motion, or it's at rest. Any of those things means the velocity is not changing. It's either constantly zero or constantly something, but it's not changing, and therefore the acceleration is zero. If the acceleration is zero, then the net force is zero. Remember the 5 things rule that we talked about. All right, so once you know the acceleration is zero, that means the net force is zero. That means the forces that add up to that net force must cancel each other out. Number 10, solve for the values of specific forces using force equations. All right, what specific forces? Well, we have weight force. Weight force, F sub g, is just equal to mass times g. Very easy to calculate. And I'm going to tell you, and I've said this over and over again, if you have a mass, immediately calculate the weight. If you have a weight, immediately calculate the mass. You'll be glad you did. You'll probably end up using one of those numbers later. The frictional force is equal to the coefficient of friction, or the frictional coefficient, mu, times the normal force. If you know mu and you can determine the normal force, you can calculate the frictional force. And the opposite is also true. If you know the frictional force from other information and you know the normal force, you can calculate mu, the coefficient of friction. In general, if you don't know the coefficient of friction and you don't know the acceleration, but you do know the mass and you always know g, the best way to solve these problems is to first solve the weight, F sub g, use that information to tell you what the normal force is, and then if you have mu, the coefficient of friction, calculate the frictional force. And now you have 3 of the forces. It'll make calculating your net forces in the horizontal and vertical direction much, much easier. All right, so now you solve for any remaining forces or remaining net forces. This allows you to solve for the acceleration or coefficients like coefficient of friction. If there is an acceleration in that direction, remember it's Newton's second law. Net force equals mass times that acceleration, or the acceleration equals the net force, that's the same as the sum of forces, divided by the mass. So these are guidelines. Every problem is going to be a little different, but these will help you solve most of these force problems using free body diagrams and the force formulas. All right, so let's look at what the formulas are. I've already mentioned several of these already, so there's really nothing new here. The gravitational force, meaning the weight of an object when it's near Earth. Why do I keep saying when it's near Earth? Well, when we have a more complicated formula when objects are further from Earth, or if we're talking about whole planetary or moon bodies and their gravitational attraction between each other. So this is the formula, the simplified version of a formula for gravitational force for something that's close to Earth, and we call that the weight. So the weight, F sub g, is equal to just mass times g. G, we're going to say, is 9.8 meters per second squared. In some problems on some tests, we might tell you it's okay to use a rounded version of g of 10 meters per second squared, but usually you're going to use 9.8. You'll notice it's not negative 9.8. We add the negative after we determine the direction of that force. And of course, weight force is pointing straight down. That'll eventually be labeled as a negative force. But when we calculate it, we calculate everything positive first. Frictional force, as I mentioned already, is mu. That's the coefficient of friction. And it doesn't matter whether it's the coefficient of static friction, which is the friction when you're first starting to move an object, or the coefficient of kinetic friction, that's when the object is already moving. Those are 2 slightly different values, but it doesn't matter to your calculations. It won't change anything for you. And then you multiply that times the normal force that you have to determine. The normal force will often be related in some way to the weight force. The net force, as I mentioned already, is equal to the mass times acceleration. This is Newton's second law. And just rewriting that, it's acceleration equals net force divided by mass. You're going to use this repeatedly, so please make sure you're comfortable with this formula. And remember, any net force is the same as the sum of forces. And I'll say it one more time, good habits to get into. If you have a mass, calculate the weight immediately. If you have a weight, calculate the mass immediately. And for either the x direction, that's horizontal, or the y direction, that's vertical, if you're given an acceleration, calculate the net force. If you are given the net force, usually you're going to have to determine the net force. But once you do, use the net force and mass to calculate the acceleration and do that right away. And then the last formulas on there don't apply to this course, but if you are interested in how diagonal forces are broken up into component horizontal, that's x forces, and vertical, those are the y versions of the forces, the y components, this is how you do it. You take the original force, multiply it by the cosine of the angle that the force is making with the ground, with the horizon, and to get the horizontal component of the force. And to get the vertical component, you multiply the original diagonal force times the sine of that angle. And at the end of this lesson, we actually have a section that's advanced on using these trigonometry methods to determine component forces. But again, you're not required to know that for this course. All right, so let's take a look at some of these force problem examples. The first example is an example of horizontal motion in a force problem. It says, number one, Lily applies a 200 Newton force in a positive horizontal direction. Okay, what does that mean? It means she's pushing it to the right. Okay. And it says it's applied to a 40 kilogram box. What does that tell you? Well, if you see kilograms, remember that's the unit for mass. So 40 kilograms is your mass. So we'll write that down. Mass equals 40 kilograms. What else do you know? Well, it's resulting in the box moving to the right at a constant speed, moving at a constant speed to the right. What does that tell you? It's a constant speed to the right. That's a constant velocity. Therefore, there's no change in velocity. Therefore, the acceleration is 0. Therefore, the net force in the horizontal direction, which is the same as the sum of the forces in the horizontal direction, is 0. So we already know quite a bit about this. And she's applying this force. So this is an applied force of 200 newtons. And it's to the right, so we know it's in the positive direction. We'll just make a note that it's in the positive direction with a little parentheses and positive. All right, so let's draw a free body diagram. Now we could draw a box and we could draw the ground, and that's fine to do that, but there's no reason why you just can't imagine the box as just a dot and say, what are all the forces on the box? Well, we know there's an applied force. We're told that right away. There's an applied force. And it's to the right. So we know that's in the positive direction. We'll make a little note that it's positive. We also know the box has mass, and therefore, since it's on Earth, it has weight. So we have a weight force. We absolutely know that. And we know that weight force is equal to m times g, which we could calculate immediately, but we'll wait a second here. We'll calculate it soon enough. If there is a weight force, and if that was the only vertical force on this box would start accelerating because it's a net force. If that was the only force composing the vertical net force, it would start accelerating towards the center of the Earth, but that's obviously not happening. The box is not soaring down into the earth or soaring up into the sky. The net force in the vertical direction is 0. How do we know that? Because it's not moving in the vertical direction at all, and therefore it's not accelerating in the vertical direction. And if it's not accelerating in the vertical direction, the net force in the vertical direction is also 0. So we know that this force must be balanced by some other force. Well, the force that it's balanced by is from the floor up. It's the normal force preventing the box from penetrating the floor. And we'll remind ourselves that's a positive force, and the weight force is in the negative direction. But we also know the horizontal net force is 0. But we only know about the applied force. If the applied force is the only force, that box should be accelerating. It should be going faster and faster and faster, but it's not. It's moving at a constant velocity, which means there must be a balancing force that completely balances the applied force. It has to be something in the opposite direction of the applied force with the same size. Well, the obvious choice for this force is friction. The box is rubbing against the floor. So we have our forces that make up our free body diagram. There aren't any other forces that are either mentioned or implied here. And now we're ready to start calculating. We know the weight force can be calculated. We know the normal force is exactly the same size but the opposite direction as the weight force. And we know the frictional force is equal to mu times the normal force. Well, we know the normal force, but we don't know mu and we don't know the frictional force. So that might be an issue. We have to figure out how to solve things. All right. So let's scroll down and see what else we need to do and what can help us solve this. Well, part B asks us to make an XY table for the components of all forces on the box. Be careful to label the directions positive or negative. All right, so we have a number of boxes in this grid, and we'll look at the main 4 empty boxes here. 2 of these boxes are in the horizontal direction, and 2 of these boxes are in the vertical direction. And if you look at the labels at the top, you'll see that there is a label for the positive direction. So for horizontal, that would be to the right, and for the vertical, that would be up. And the negative direction for horizontal would be to the left, and for the vertical, that would be down. And then we're going to add the horizontal forces to get our sum of horizontal forces, also known as the horizontal net force. And then we'll add the 2 vertical, or add whatever vertical forces we have to get our sum of vertical forces, otherwise known as the vertical net force. All right, so what forces do we have? Well, if we scroll a little further down so we can see the free body diagram we made, we can use the diagram to fill in this box. Do we have any horizontal forces in the X direction? Yes, of course we do. We have a applied force in the positive direction, so we can write applied force here and remind ourselves that's positive. Of course, it says positive right there, so that's fine. And in the negative direction horizontally, we have a frictional force. And we'll remind ourselves that's negative. And frictional force can be eventually calculated with the coefficient of friction times the normal force. Though we don't have the coefficient of friction, so we might not be able to solve it that way. All right. And what's our net force? Well, our net force is just the sum of the 2. It's going to be the positive applied force, let's see if I can get that in there, plus the negative frictional force. I know I'm going outside of the box here. What are the vertical forces? Well, we have the weight force, but that's pointing down. That's our negative one. We know that that's equal to mass times gravity. We can calculate that very easily. We have the mass, we know the gravity. And we know there is a normal force that completely balances it in the positive direction. So we know the normal force is exactly equal to the gravitational force, the weight force, just in the opposite direction. So then we know that the sum of the forces is 0. So we know that the sum of the normal force in the positive direction and the sum with the negative gravitational force, we know when we add those together, we'll get 0. Just like we know for the horizontal forces, when we add those together, we also get 0 because that object, that box, is not accelerating in a horizontal direction. So we have a lot of information here. Now, what could we calculate right away? I'll use a different color here to point it out. Use light blue here. All right. We can calculate the weight force instantly. And since it's exactly balanced by the normal force, we can get that instantly. Now, can we get the frictional force from that? Well, we don't have the coefficient of friction, so we can't. But we are given the applied force, and we know that the net force, both vertically and horizontally, is 0. What can that tell us? Well, the strategy here is if we know the applied force, this force right here, and we know the total horizontal forces are 0, we could figure out what the frictional force is and use that information to get the coefficient of friction. So let's see what the question asks, and hopefully it will walk us along the pathway to solve this. So the first question says, what is the net force in the vertical direction? How do you know? Well, we've already figured out that the vertical net force, we can write net force sub y, or we can write sum of the forces in the y direction. We know the box is not accelerating up in the air or accelerating down through the ground, so we know there's no acceleration vertically, so there's no net force vertically. What's the vertical acceleration on the box? Well, we know the vertical acceleration, we'll call it acceleration sub y. We know that's 0. These two go hand in hand. If one is 0, the other is 0. All right? We know because the box is not changing movement vertically. Okay. Part E, what is the net force in the horizontal direction? How do you know? Well, we are told it's at a constant velocity. It said constant speed in the same direction. All right. Therefore, the acceleration in the horizontal direction is 0. Therefore, the net force in the horizontal direction, force sub net sub x, which is the same as the sum of the horizontal forces, we know this is also equal to 0. And we know that because the box is not changing movement or motion horizontally. That means the acceleration in the x direction is also 0. And again, these two go hand in hand. If one is 0, the other is 0. If you know anything about one, you know something about the other. All right. So this is walking you through the steps that I said were going to be important anyway. Calculate the weight of the box. Well, we know the weight of an object is just equal to its mass times g. The mass is 40 kilograms. You're told that right in the problem. You're given G is 9.8 meters per second squared. We'll multiply those together, and we get 392. Well, forces are always in newtons. When you multiply kilograms times mass, meters per second squared, you get kilogram meter per second squared, but we call those newtons. And now we make a note here. Since this is pointing down, we make a note that this is going to be a negative force. We just kind of make a note that it's negative. All right, this will save us some trouble later. Now it says calculate the normal force. Well, the normal force, which is in the positive direction, plus the gravitational force, which is in the negative direction, that equals the net force in the vertical direction. But we know that's equal to 0. Well, if that's equal to 0, then these two equal 0, which means they cancel each other. If the weight force is minus 392 newtons, and we know the sum is 0, then the normal force minus 392 newtons must equal 0, and therefore the normal force must equal positive 392 newtons. You don't have to go through the math. You could just realize, oh, it's got to balance it and it's positive, and just write it that way. But I'm showing you the formula itself. So now we know the weight force and we know the normal force and we know the applied force. So the next question is, what must be the value for the frictional force? Well, we can't calculate the frictional force using the coefficient of friction and the normal force, because we don't know the coefficient of friction. But what we do know is that the sum of the horizontal forces, also known as the net force in the horizontal direction, we know that's equal to the applied force, which is going to be a positive value, plus the frictional force, which we know is a negative value because it's pointing to the left. And we know these add up to 0. Well, we know this value, and we know what a 0 is, so we can easily figure out the frictional force. So if I just take this formula and write the numbers we know there is a positive 200 Newton force. That's our applied force. We know when we add that to our frictional force, and it's going to be a negative number. We're not saying it's negative right now. We're going to assign the negative when we're done. When we add those together, it's 0. Therefore, the frictional force must be equal to negative 200 newtons. That has to balance completely. And now we know the frictional force. Now we know the frictional force, and we also know the normal force. This will give us a way to calculate the coefficient of friction. Part J says if you needed to calculate the frictional force, you don't this time because we just calculated it. What formula would you use? Well, we know the frictional force equals mu times the normal force. Well, we know the frictional force. We know the normal force, so we can easily calculate mu. So just writing that same formula down again allows us to calculate the mu value, the coefficient of friction in this case. So we substitute our numbers. We know the friction is 200 newtons, and this is where it's really important to remember, don't assign the positive or negative just yet. Equals mu times the normal force, which we know is in the positive direction, but we're just going to write the number, 392 newtons. Now, why am I keeping these positive and negative signs in parentheses? Because mu, if I divide both sides by 392 newtons, and I'm just putting in parentheses the positive and negative signs, we get that mu is this ratio, and that works out to be 0.51. And you might say, well, wait, I've got a negative divided by positive. No, we don't assign those until you're done, because mu is always a positive value. It's always a positive value, and it's always a unitless value. Why is it unitless? Because we have newtons divided by newtons. They cancel each other out. Mu, the coefficient of friction, is a ratio. Ratios of the same type of units are unitless ratios. So this is a unitless value. It's one of the few that you're going to have in this course that has no unit. And that completes problem number 1. Number 2. Now Lily applies a 450 Newton force. Okay, they're telling you the applied force right away in a positive horizontal direction. Okay, you know which direction it is, to the same 40 kilogram box. Okay, you know the mass too. On a different floor. This time the box accelerates to the right. All right, so it's accelerating. This is something different. And you're told the coefficient of kinetic friction, mu, is equal to 0.34. Okay, why does it say kinetic? Because the box is already moving, so we use coefficient of kinetic friction, meaning moving friction, as opposed to the coefficient of static friction, which is the standing still friction when you're just getting the box to start. It doesn't change anything. You can ignore the words static and kinetic in this case. It's just coefficient of friction. All right. So we have a similar situation, but now the box is accelerating and we know the mu value. So what else do we know? Right from the problem, we know the applied force is equal to 450 newtons, and we'll make a note that it's in the positive direction. We know the mass is still 40 kilograms. We know G is 9.8 meters per second squared. And we know mu is 0.34. Mu is almost always going to be a number between 0 and 1, and it will have no units, as we just mentioned. Okay, so we have 4 pieces of numerical information already, and we know there's an acceleration. The acceleration is to the right, so we know the acceleration is positive. So we know a lot about this. All right, let's start drawing our free body diagram. We'll draw the box on the ground as if it's just a dot. We know there's an applied force of 450 newtons in the positive direction. We'll just write that, and we'll just make a note it's in the positive direction. We know the box has weight. Anytime you have an object that has mass, it's going to have weight. As long as it's on the earth or on the moon, it'll have less weight, but it'll have weight. We can calculate this later as m times g. We know there's a normal force balancing the weight force because that box isn't flying up into the air and it's not flying down to the center of the earth. Okay, but we know the box is accelerating to the right. Is that the only force? Well, it might be, except we're literally told that there's a coefficient of friction, so there must be friction. And friction is always in the direction opposite of motion or potential motion. Well, the motion is to the right, so friction must be to the left. And you'll notice I'm making a relatively small arrow because we know this arrow has to be bigger than the frictional arrow because it's accelerating to the right. We're just making a note, it's accelerating. This is not part of the free body diagram. That's just a note to yourself saying, hey, I know it's accelerating, so I know that there's a net force in the horizontal direction. All right, so we have our free body diagram, which is going to be very helpful for calculating everything. We can make a note again that our our frictional force is just equal to our coefficient of friction times our normal force, and everything else should be pretty straightforward. So let's take a look at the table we have to make and start filling it in. What do we know? We have the horizontal forces in this row and the vertical forces in this row. And so our horizontal forces that are in the positive direction, the only force in the positive direction is the applied force. We'll make a little note that it's in the positive direction. The force that's in the negative direction horizontally is our frictional force, and we'll make a note that that's in the negative direction, and we can calculate that as mu times the normal force. Well, we have mu this time, so that's useful. And the sum of the forces, also known as the horizontal net force, is just adding those two up. We literally just add those up. Oh, it's the applied force in the positive direction plus the frictional force in the negative direction. It's supposed to be a negative. And we know that's not equal to 0. We know that's equal to something else. But remember, having the net force, this is also called the net force in the horizontal direction, having a net force allows us to calculate the acceleration later. All right. And if we look at the next row, the vertical forces, we know there's a upward force that is the normal force, and we know there's a downward force, I'm writing it as a negative force, is equal to weight force, and that can be calculated as m times g. Our sum of forces, which we know is 0, is equal to the sum of these two forces, our normal force, which is up, and our weight force, which is down, labeled negative. And those two forces equal 0, so they're going to cancel each other out, which means they are the same size. So once we calculate the weight force, it will tell us what the normal force is in the opposite direction. So we've already got an enormous amount of information that will really help us do all our calculations at this point. All right, so what are we asked for? Well, we're asked for what is the net force in the vertical direction. Well, we know the net force in the vertical direction, which is the same as the sum of the forces in the vertical direction, is 0. How do we know it? Because there is no net acceleration in the vertical direction. Acceleration in the y direction is 0. Why? Because the box isn't changing vertical motion. In fact, it's not moving at all vertically. I said movement before, motion means the same thing. And that answer really covers this answer as well. These two always go hand in hand. For the horizontal direction, is there a net force? Yes, there is. How do I know there is a net force? Because there is a horizontal acceleration. If there's a horizontal acceleration, there has to be a horizontal net force. If there's a horizontal net force, there has to be a horizontal acceleration. They always go together. Calculate the weight. Remember, I said you're going to be doing this a lot, so just get into the habit. Because you're not going to get all these prompts in a problem. They're going to ask you to solve everything. So I'm walking you through step by step, but on an exam problem, you would just get the initial problem, the wording problem that you saw at the top, and then they'd say, okay, what's the acceleration at the end, or what's the coefficient of friction at the end? So you have to do everything yourself and fill in the table yourself. Well, we can easily calculate the weight force. We know the mass, 40 kilograms. We know the gravity, 9.8 meters per second squared. And we end up with the same weight as we did with the last problem, which we know is in the negative direction, and that's 392 newtons. Let's not worry about the sign just yet. Okay. And then we're asked to calculate the normal force. Well, just using logic without actually calculating, we know the size of the weight force is equal to the size of the normal force. So we know the normal force is also equal to 392 newtons. It's just in the positive direction. And this is a much easier way to do it than using formulas, but I wanted you to see both ways. Okay. So now we know two forces. We know the weight force. Actually, we know three forces. We know the weight force, we know the normal force, and we know the applied force. Using the value for the coefficient of friction, which we know, if we scroll back, we see the coefficient of friction is 0.34. 0.34. Calculate the frictional force. Well, the frictional force is mu times the normal force. Well, that mu is 0.34, no unit, and the normal force is 392 newtons. And you'll see I didn't bother putting the positive sign in there. And when we multiply these together, we get 133.28 newtons. And now we assign a direction to the force. We know it's a frictional force, which is pointing to the left, and now we assign that it's a negative. So this is why we don't bother putting in a positive or negative sign in the calculation. We wait till we're finished to assign an actual direction. So now we're going to start to calculate the acceleration, but first we need a net force. We know the vertical net force is 0, but that's not important to the horizontal acceleration. So we need the net force in the horizontal direction, which we know is the same as the sum of the horizontal forces, and that is the sum of the two forces that we know are moving horizontally. We have a positive direction applied force and a negative direction frictional force. And we know the values of each of these. The applied force is a positive 450 newtons, and the frictional force is a negative 133.28 newtons. And we just add these up. One is positive and one is negative. It's very important at this point to have the directions, and this sums to 316.72 newtons in the positive direction. And why is it the positive direction? Because there has to be a net force in the positive direction for us to have a net acceleration in the positive direction. Well, the acceleration is easily calculated once you have the net force in the x direction. We divide that by the mass. Acceleration equals net force divided by mass, and technically we're only looking at the acceleration in the x direction. If you want to label x, that's fine. And now we plug in our numbers. We have a net force of positive 316.72 newtons. Our mass, which we've known from the problem itself, and now it's just a matter of pulling out your calculator and doing a little division, and you get positive 7.918. And you might say, what's the unit? Well, it's an acceleration, so we know our units are in meters per second squared. And if you want to ask yourself, why is that? Remember, a Newton is just a kilogram times a meter per second squared. So if I take kilogram meter per second squared and divide it by kilogram, the only thing I'm left with is meters per second squared. But you don't have to remember that. You just have to remember the units for acceleration are meter per second squared, and make sure you have your number and make sure you have your positive sign. And that's it for this problem. Okay, let's look at one more horizontal motion problem. Number 3. Alicia applies a 443 Newton force to an 87 kilogram refrigerator on the floor. Okay, what do you know so far? You know that there's an applied force of 443 newtons, and you know that the mass of the refrigerator is 87 kilograms. So we can immediately take little notes. Our mass is 87 kilograms. Our applied force is 443 newtons. We don't know the direction just yet. It says the refrigerator accelerates at 2.06 meters per second squared to the right. Okay, well, we know the applied force must be to the right, so we'll just label it with a positive there. We know the acceleration is to the right, so it's also positive, 2.06 meters per second squared. And now we write our free body diagram. Well, we could draw a refrigerator on a floor, but let's just make a dot. Okay, we know there's an applied force to the right. We know how big it is, so we don't have to calculate it. We know that there's going to be an acceleration, so we can just make a little note there's an acceleration, but that's not part of the free body diagram. We know this thing has a weight, probably a big heavy weight, and that weight is easily calculated as the mass times gravity, and we know the mass. We know the refrigerator is not flying up into the air or accelerating down to the center of the earth, so the normal force must be balancing it perfectly. That's a positive direction vertical force, and the weight is a negative direction vertical force. Our applied force is in the positive direction. Okay. Do we know about any friction? Well, there might be friction, but there's nothing mentioned about friction. So we have to start doing analysis to see what's going on. So the next part of this problem is to fill in a table. We fill in our XY table as always. What values do we know? We know for sure there's an applied force in the positive horizontal direction. We know for sure this thing has weight. Has weight, which we'll put in the negative vertical direction. And that weight is mass times gravity. We know there's a normal force that's balancing it to keep the refrigerator from falling down to the center of the earth. And we know the net vertical force is 0 because it's not flying up or soaring down to the center of the earth. So we know that these two forces balance each other perfectly. And we know that this 0 adds up, is the sum of the normal force in the positive direction, plus the negative weight force. We know that the horizontal forces are equal to an applied force in the positive direction, but it might not be the only force. There might be friction. How do we know if there's friction or not? Well, this is what's interesting. We are given an actual value for the acceleration. We're actually given the acceleration, and we're given the mass. So we can immediately calculate mass times acceleration, which is equal to the net force in the horizontal direction. If that net force in the horizontal direction is not simply equal to the applied force, there must be other forces added. So the question says, using your knowledge for calculating each specific force and the net force, what is the coefficient of kinetic friction between the refrigerator and the floor. And it's called kinetic because the object's already moving. All right. Now, before you solve this part of the question, you might have said, well, I don't know how I could have calculated that the net force was a different number than the applied force and used that to figure out that there was a frictional force. Well, we tell you in this part of the problem, there is a frictional force. And how do you know? Because we're asking you for the coefficient of kinetic friction. So if there's a coefficient of some kind of friction, there must be a frictional force. So we'll go back to the table and add that value in to complete the table for negative direction horizontal forces, a frictional force, and as you already know, that's equal to the coefficient of friction times the normal force, and eventually we're going to be solving for that coefficient of friction. Okay, so we have our table, and now it's a matter of doing the calculations. So it says using your knowledge for calculating each specific force. All right, so which forces do we know? Well, if we scroll back to what we already wrote down here, we've got this information, these four pieces of information: G, M, A, and an applied force. So from this, we can calculate several other pieces of information directly. All right. So we'll quickly write down what we already know. We know that the mass is 87 kilograms. We know the kilograms. We know the acceleration is positive 2.06 meters per second squared. We know G is 9.8 meters per second squared. And we know the applied force is in the positive direction, and that has a value of 443 newtons. Okay, so we have a lot of information at this point, and we immediately know that we can calculate the weight. The weight is equal to mass times G, which is 87 kilograms, times G, 9.8 meters per second squared. We pull out our trusty calculator, and we determine that the weight is equal to 852.6 newtons. And we make a little reminder, it's in the negative direction. All right. The normal force is the only force balancing the weight force. So we know it must be a positive direction, 852.6 newtons. Great, we have two forces. We have three forces already now, so we're doing really well at this point. We know that the horizontal net force, also known as the sum of the forces in the horizontal direction, is equal to the applied force, which is in the positive direction, plus the frictional force in the negative direction. We can't calculate the frictional force from mu because we don't know mu. We're actually asked to calculate mu. It's asking us what is the coefficient. So we have to determine the frictional force first, and we can use information from our net force to figure it out. Now you might say, okay, well wait, I don't know this value. I know this value, and I don't know this, and I don't know this. There's two things I don't know. But what you do know is that any net force is always equal to the mass of the object times its acceleration. So it's very important to remember this net force in any direction, horizontal or vertical, equals the mass times that acceleration. So if this is the net force in the x direction, it's the horizontal acceleration. And this is the horizontal acceleration, so I'll label that a sub x. All right? So we can actually calculate what the net force is by multiplying mass times the acceleration that we know. And we plug that in. We've got 87 kilograms, and we multiply it times positive 2.06 meters per second squared, and we get that this equals a positive direction force of 179.22 newtons. So now we know the sum of the forces, this number, and we already know the applied force, that number. It's pretty straightforward to calculate the frictional force. So let's slide down to have a little more area to work in. And I'll try to write small because it's taking up too much room on the screen here. But we know that the net force in the horizontal direction equals the applied force. Applied force plus the frictional force. We know the net force is equal to 179.22 newtons. We know the applied force is equal to positive 443 newtons. And we don't know the frictional force. Well, we subtract 443 from both sides, 443 newtons from both sides, and we end up with negative 263.78 newtons is our frictional force. Well, frictional force equals mu times our normal force, and we know the value of our normal force. Our normal force is 852.6 newtons. Mu we don't know, and our frictional force we just determined as being 263.78 newtons in the negative direction. Now, you'll notice I am putting the frictional force's direction in parentheses. That is because mu, the coefficient of friction, is always a positive value. So we want to divide both sides by this number, 852.6 newtons. 852.6 newtons. I know I'm cramming everything in. I'm going to write it up here. So when you divide these two numbers to get mu, these two will cancel, you get a value of mu that is equal to 0.309. The newtons cancel the newtons. Mu is always a positive value and it has no units, so our final answer is that the coefficient of kinetic friction is 0.309, and that's it. And that completes the horizontal motion force problems.